Hello everyone, my name is Chen. Our work is about specification inference for Linux interfaces. So this is a joint work with my collaborators at the Hong Kong University of Science and Technology and is supervised by Professor Charles. So Linux is a monolithic kernel and it has vast code bases and integrates numbers of subsystems such as file systems and drivers. These subsystems are developed and collaboratively by different parties, and we're treating Linux as a whole kernel. It interacts with user space and hardware and receives data from these two spaces. So from the security perspective, we usually treat this data from user space and hardware space to be malicious, so we need to carefully check them before using it. So to speed up the development and easier communications between different subsystems, Linux utilizes interfaces to standardize their interactions. So there are often two roles centering around the interfaces, invokers and implementers. So to achieve certain functionality, the invokers pass some data to implementers and receive the process result. So in Linux codebase, the interfaces have two forms, function pointers and APIs. So here are some examples for the two forms of interfaces. First, function pointers abstract common operations among a set of subsystems, and one function pointers could be implemented by different subsystems to handle their own unique features. And the caller could just call the function pointers and ignore the underlying differences among them. So for instance, the USB drivers can allocate their own resources when implementing the probe function pointers. And the caller can just invoke probe to initialize the USB drivers uniformly. And second, Linux provides a lot of APIs for common functionalities and avoid code duplication. For instance, we can use this API to allocate memories and use another API to retrieve IRQ from devices. So considering the extensive data exchanges between invokers and implementers, we define interaction data as a variables that is defined and initialized by one party, but also visible and used by another party. So in that case, when the invoker only focuses on how to use these interfaces, or when the implementers only focus on how to implement them, the developers would only have the local context and would be unaware of the risks of the interaction data and subsequently mishandle them. So to ensure the correct manipulation of interaction data, we have the interface specifications to declare the rules that both parties should follow when manipulating these data. So we give an example of interface specification to ease your understanding and make sure that we are in the same page. So first, the invoker I² C sub SM bus transfer calls the interface SM bus transfer at line 20 and pass the interaction data, which is a variable data here, as arguments to the implementer. So the parameter is later used at line 9 as the loop boundary, and the parameter, which is quite risky if this value is unbounded. So the specification for this interface contains three questions. Should the interaction data be checked or not, and who should take charge of the checking and how to check it? So since the interaction data is controlled by the user space, the answer is yes. The implementers should check the length field of data, and if not, the out-of-boundary bug would occur at line 10. So except for the security checking, the interface specifications could also regulate the usages and implementations of interfaces from other aspects. So for instance, when using APIs, the invokers should follow the requirements of arguments and understand how to handle the return values and potential errors inside these APIs. And similarly, the implementers should know how to handle the incoming parameters and produce correct return values, so on and so forth. But however, in reality, the interface specifications are often lacking. So on the one hand, the Linux developers tend to explain the functionalities of interfaces, but they do not stress the correct way to manipulate this interaction data. And on the other hand, when compiling the Linux kernel, which is written by low-level C language, only type safeties could be ensured, but the behaviors of this interaction data remain unchecked, so which could lead to vulnerabilities. And it is really hard to manually summarize these interface specifications due to the number, since the number of interfaces are huge and the behaviors of interaction data are diverse. And moreover, sometimes the specifications cannot be determined individually and need to be discussed collaboratively by the community. So to address this problem, there has been a lot of work trying to automatically infer interface specifications. So they use code bases or the patches as inputs and can be classified into 3 lines of work. However, none of them could offer comprehensive and precise specifications. So first, pattern-based approaches notice that some code patterns can be used to infer specifications. So with this observation, this work first summarized the code patterns manually by reviewing the code samples, and then they match these patterns into the whole program. And obviously, this work has poor granularity since the code patterns are often empirically determined and would overfit the code samples under inspection. Another line of work is deviation-based approaches. So they try to support more interfaces and data behaviors. Their high-level idea is that the majority of usages of the same interaction data is correct, but the outliers are buggy. So in that case, they share a general workflow by first clustering these comparable codes, calculating the similarities among them, and finally, they identify bugs with threshold. Unfortunately, this work still suffers from poor generalities and also low accuracy because the common belief may not be reliable sometimes, and both the cluster and similarity algorithms are tailored for certain behaviors. And last, patch-based approaches try to overcome the aforementioned unreliable Oracle issues by utilizing security patches as input. So starting from the code changes, patch-based approaches first locate the bug-related statements from the code changes and then use them to form the specifications. But however, existing work employ naive specification representations and fail to apply to diverse code fix patterns. So they still cannot offer satisfactory generalities and precision. So here comes our solution SEAL, which try to infer diverse and precise specifications from code changes in security patches. So it follows the patch-based work and choose code changes as input because the correct usages are indicated in the patches, and its vast numbers could offer a wide range of interfaces. So the output of SEAL is the interface specifications that regulate the usages of interaction data as we exemplified before. But there are still some challenges to mine specifications from patches, mainly from 2 reasons. So first, the bug-related statements are buried sparsely inside or even beyond the patched functions. And also, there could be only a few lines of code changes inside a security patch, such as less than 10 lines in the extreme case. So in this case, it is very hard to locate all the bug-related statements to form specifications. For example, here, this patch fixed the previous out-of-boundary bug by adding a security check at line 8. So starting from this code check, we should identify that both line 9 and line 10 are bug-related statements. And moreover, to support the diverse behavior of interaction data, the specifications should be carefully designed to be as expressiveness as possible. So to tackle these 2 challenges, SEAL proposed to use value flow passes as the central data structure when identifying the bug-related statements and forming specifications. So value flow passes track the movement of variables along statements. it has been used to detect various bugs in the field of static analysis. So specifically, when we want to detect some bugs, we can describe the critical rules should be followed with value flow properties. So once such properties are violated, we would report that there is a bug. So these properties mainly contains like source statements, sink statements, and also the conditions for the passes from source to sink. So with these properties, we can check bugs with reachability analysis. So for example, the property to avoid non-pointer dereference is given here, so in which the source is the return value of malloc or some other allocation APIs, and the sink is a dereference set in the load or store statement. And the condition is that the reachable path from source to sink should not exist when the malloc return non-pointer. So based on the value flow passes, SEAL proposed to formalize specifications as value flow property, which contains the rules to be followed. And with this idea, SEAL first analyzes the patches. It first maps the source code changes to the value flow path changes by compare the program dependence graphs for the codes before and after applying the patch. So when compare these two graphs, we want to thoroughly capture all the bug-related statements. So SEAL proposed to compare the passes in 3 dimensions, which is data dependence, control dependence, and also the execution orders of statements. So for the patch examples we have shown before, after the PDG comparisons, we could understand that although the value flow path of the block field of data is unchanged, its path conditions is altered, where a new logical expression phi3 is conjectured. So this is a changed path condition. Then, with the changed value flow passes, SEAL starts to form the specifications with generalization. So the general idea is the changed passes are essentially instances of the specifications. So to obtain these specifications, we reversely generalize the passes. Specifically, SEAL first ignore all the local variables that is specific to the patched function, but retain all the interaction data. And then for this interaction data, SEAL generalize them to expressions so that we can use these expressions instead of variable names to find bugs in other code regions. So for example, the variable data here is generalized to the second parameter of interface SM bus transfer. So regardless of other implementations of the interface, their name is not their name doesn't matter, but we only consider their argument index. Similarly, the sink dereference set is abstract to a dereference expression. And we perform the same generalization to the changed conditions of value flow passes. And finally, SEAL would deduce the quantifiers of reachability relationships by inspecting the patched code. So due to the time limit, you can find more details of our algorithm in our paper. And the last step is how can we use the summarized specifications to detect bugs. So with these specifications, the bug detection region is essentially other usages or implementations of the same interface. So to this end, SEAL first locates the source and sinks and variables inside the target codes by matching the expressions in the specifications to the code regions. And then SEAL search for value flow passes from the source to sink and check if the specifications are followed by these value flow passes. So still for the same specification, since the matched source could reach the sink without a critical check, SEAL would report there is a bug. And this bug is already fixed by our patch assigned with CVE ID. So in summary, the general workflow of SEAL is given here. Please refer to our paper for more details of our careful design of the specification and the inference algorithm. So finally, let's quickly review the evaluation of SEAL. To mine specifications, we collect over 10,000 security patches from the historical commits of Linux. We use some keywords to filter out applicable patches, and the bug detection target is Linux version 6 to 6.2. So let's first see the effectiveness of SEAL in terms of bug detection. So SEAL identified overall 167 true bugs, including 95 of them being confirmed and 56 of them being patched, which is quite amazing. And you can scan this QR code if you are curious about the bugs found by our tool. And our found bug could be classified into 9 types, and they have been hidden over 7 years, which is quite a long time before being introduced. And SEAL could attain a precision of around 70% during the bug detection phase. And here are the list of bug types and root causes of reported bugs. Let's also zoom into the correctness of the generated specifications. So SEAL produced around over 10,000 specifications from these input patches with a precision of around 60% after we manually checked some samples from it. And we also choose 2 representative existing work from Usenix to compare with it. And it turns out that SEAL could outperform them in terms of supported bugs and precisions. So in summary, SEAL targets for the interface specifications, which are quite necessary to ensure the correct manipulation of interaction data, and it exploits the expressiveness of value flow properties to represent the specifications. And in the end, we also want to deliver some suggestions to Linux community during the journey of designing and implementing SEAL. So first, we recommend the Linux communities to actively run SEAL or some related works to generate specifications when new patches are applied to complement these missing specifications when the APIs or the interfaces are designed. And inexperienced developers are suggested to learn from existing patches to understand how to use or how to implement interfaces in a correct way. So that's all for my work, and here are the QR code for our paper, found bugs, and also the open source code. And if you have any questions that cannot be asked today, feel free to drop an email to me, and I'm happy to take any questions.
Thank you for the talk.